Hey, welcome back. In this session, we are going to learn about big O notation and what it is and how we can apply it. Basically, big O notation is a measurement for the performance of your algorithms. And there are different let's say, levels of the complexity or levels of performance for your algorithms. There can be a level of constant time. It means that regardless the size of the task, it will be accomplished at a constant time, right? There will be a specific fixed number of steps that you need to take to perform the operation. It's the best performance you can get. Then you have a logarithmic time. We are going to look into the examples of logarithmic time algorithms a little bit later on, so don't be too scared. And there is a linear time. Let's actually look at the constant time, which is this one. So the purple line here, which doesn't go higher, you see it's just 1, and regardless of the input size, which is this small n here, it will always remain the same. Then the next best one is actually logarithmic time, this dark blue, as you can see here. And linear time is this one, so the one that goes straight to the upper right corner, which means that, for example, if your input size is 50, it will take your 50 operations. So it's directly proportional to the number of elements. So if you, for example, pass a bigger array, you will expect the algorithm to do more steps as well. This time complexity is considered okay for most algorithms, and for some actually you would prefer, for example, a 1. And we are going to see a couple of examples in a second. So the next one is linear arithmetic time, which is when you get this log n you've already seen before, and multiply it by n. Once again, we are going to see examples of such algorithms, but maybe right now, just theoretically, it's a little bit harder to understand. So I'll go to the quadratic time. It means that, so it's actually here, as you can see, this orange line, so it goes straight up, right? So for example, if you have 10, it's already 100 operations. So for each it's not even for each, it's basically multiplying the input size by itself, then you get the quadratic time, which is crazy. You see this n squared. Let's say the exponential time is even worse, and factorial time, which is this n factorial, is even worse as well. Basically, the idea behind big O is to give some measurement to the algorithms. So it's like a scale, a meter, or I don't know, like a temperature meter that measures the performance of the algorithms. Why do you need that? You need that to be able to compare two different algorithms and tell which one performs better without even running it, right? You can just look at the code and say, hey, okay, this algorithm is better. The next thing is that you don't only can use this big O for the number of operations, so for the speed with which your algorithm is performing, but also the space complexity or the amount of memory it takes for the algorithm to complete. We are going to see a couple of examples once again. So right now I'm going to go to the Xcode and we are going to explore a couple of examples. The first one would be the constant time. So here the constant time, which is 01. And as I said, algorithms have the same running time regardless of the input size. For just look at this function. check first and names. The names can be a small array of 3 elements, or maybe 1 element, 0 elements, or it can be hundreds and thousands of elements, but this function will always perform exactly the same amount of steps. First, it will check if there is a first, name, right, in the array, if there is 1 element at least, and if it is there, we're going to print it. Otherwise, we are going to print no name. So this function time complexity would be O1, right? So it's constant time. Now, if we go further, for example, for linear time, so this is a linear time. So algorithms have a running time directly proportional to the input size. So for example, if we have an array of names, here you see a for loop, you see, so depending on the size of names, we will have also different amount of for loop iterations, right? So for example, if names have 3 elements, our algorithm will also perform 3 operations. If the names is like an array with 100 elements, our function will perform 100 operations. As you can see, it's directly proportional, and that's why it's ON. By the way, whenever you see like a for loop, you can already like, oh, ring a bell, it's a ON time probably, so it's a linear time, right? The next thing is I want to show you one characteristic of the big O, and it is that it is not exactly precise. Because maybe you have seen it here, so it is precise enough, let's say, right? So it's levels of complexity, not the exact complexity. What I mean is that, for example, here we said it takes always one, so it's O1, right? But as you can see, we do at least 2 operations each time. So we check if, and then we print, or we check if and then we print here. You see, we actually did 2 operations, not 1, but we consider it O1. Same thing here, for example, if we have 2 for loops here, you could say, hey, okay, this is an n, this is an n, so together it's 2n. But actually, big O notation disregards the constants, the multipliers, let's say, of the variable. So it's not actually 2n here. It is just 1n here. So you would disregard it, right? Or for example, if you have so here you see this is an operation, right? And here you could say, or maybe I would do something like, for example, if let first equals names first. So I'll add a constant time operation here. You will not write on plus 1, right? You always disregard like the smaller part. Or for example, if you have more difficult complexity, like for example n squared, we're going to look into example right now, you will not write n squared plus n, right? You will disregard the smallest part, the less significant part, right? So all right, so that's it for like this little rule, let's say. As I said, just to reiterate, so for example, if you have on squared plus n, it is simplified to on squared, as I just said. Or for example, if you have constant multipliers, O3n is simplified to on. All right, so those 3 things are done. Now let's have a look into the quadratic time complexity. So here, quadratic time complexity is when you have n squared. So, or n in the power of 2. Quadratic time algorithm have a running time that's proportional to the square of the input size. Here's the example, for example, quadratic example, for example. Yeah. So here you have for loop inside another for loop, right? You can prove how it works, basically. But just know whenever you see for loop inside a for loop, it's a quadratic time automatically. For example, let's have names. I will put 3 elements here, A, B, and C. And I will also count the elements. And here, for example, I'll say count plus 1. And here, so what I want to measure is actually the amount of times the function is going to run. So print names, I just wanted to print count. you'll see that it's going to be 9. It should be 9, right? And, or actually it's 0 because I didn't call it. Print names, quadratic names. Okay, as you can see, it's 9, and you know that 3 squared is 9. So we just proved that this function has quadratic time complexity. All right, so the next one would be to explore actually the space complexity. So the space complexity, here's the example for it. You apply the same kind of principle, so the same notation, but to a different area, let's say. So here, for example, we know that this function takes so its time complexity is O(n), but look at this. Now we use an extra variable, and this variable is an array. And the size of the array, so the size of the memory we want to use for this algorithm, will be also, as you can see, proportional to the size of n. So here the space complexity would be O(n) as well, because at the end we are going to create an array that would take up n elements, right? So the space complexity for this algorithm will be O(n). If you want to look into different other space complexities, so here we don't do anything at all, especially if I remove this one. So we don't have an extra variable, so it would be constant space complexity, so O(1), even though the time complexity is quadratic. Then here we also don't create any extra variables. It's O(1) here, and here it's also O(1) because this thing is just one element and is not proportional to the size of the array. But as you can see here, we created an extra array of n elements, and it means that we have space complexity of n. And for example here, if we would like to store all the results, right, names equals string, and here we would append them, so names append name, then the space complexity for this function suddenly becomes O(n) squared. All right, so, or quadratic. All right, so that's it for the introduction to big O(n). So big O(n) actually, yeah. Or just big O. And we are going to look into more examples with more complicated algorithms. You'll see logarithmic time, linear arithmetic time, things like that, and you would get a better understanding. But before we do that, I want you to try to solve a problem yourself. Please pause the video when you see it. So here's the function, and you can read what it does and try to analyze it. And yeah, you can make a pause right now, think about it, and continue when you have a solution. All right, so let's analyze it together now. So here we have a for loop, right? And it already rings us a bell that we have O(n). So then we have two sets, right? Scene and duplicates. And we don't know yet which size there will be, but this would give us already O(n) time complexity, right? Here, for example, we do one operation, and you see, so we either add an element here or here. So together, they would give us O(n) space complexity. So I would say, for example, here it would be O(n) divided by 2, and here O(n) divided by 2. But since division by 2 is a constant, we would just get rid of it, right? And I would say at the end we have time complexity O(n) and space complexity 2. Space complexity O(n) 2. All right, if you got the same result, congrats. If not, don't worry, I think you will get better at it when you see more examples. All right, so that's it for this session, and we'll see each other in the next one. Ciao.